Hello everyone, I'm Harper Carroll and welcome to Harper Carroll AI. Today is day 5 of the 10 days of AI basics, and today we're going to go over training processes. I'm super excited about today's video. It, as I said, is day 5, so if you haven't watched the other videos, make sure you check them out. They're really important context. If you just want to learn about, iterations and epochs and batches, let's actually just watch this really quick 90-ish second video that I made on Instagram and TikTok. Hello, welcome back to the 10 Days of AI Basics with Harper Carroll. If you don't know me, I got my undergraduate and graduate degrees from Stanford University in computer science, focusing in artificial intelligence, and I was at Meta for 4 years doing AI. Today is day 5, and we're going to be talking about training processes. So we're going to learn about epochs, batching, iteration, and validation. First, let's talk about epochs. So epochs are a full pass through the entire training data set. So for example, if our training data set were a book, it would be a full pass, cover to cover, front to back. This means the model has seen every single training data example provided. Next, we have iterations. And iterations are often used interchangeably with epochs, but they're actually slightly different. An iteration is one update of the model's parameters based on the data that it's seen. And so if you have them be equal, that would mean going through an entire epoch, all the training data per iteration, per update of the model's parameters. But sometimes that is not very efficient because you have a lot of training data. So what you do is you divide the training data into batches, which are small subsets of the entire training data set, and you use one batch per iteration. Validation is when we periodically test the model's performance on a withheld validation set, which is a separate set of data, and see how the model is doing. So we can monitor for overfitting, which is when the model learns the training data too well, including its noise and errors, and doesn't generalize to new data very well. Stay tuned for day 6 and let me know in the comments if you have any questions or clarification points or whatever else you want to learn about AI. So hopefully that is helpful and a good start to today's lesson, but let's dive in. So epochs, so we defined them before, but again, it's a complete pass through the entire training data set. So it's, again, cover to cover of a book. And having multiple epochs allow the model to refine its parameters with each pass. So remember, we talked about iterations. Each iteration is one update of the model's parameters. And again, the model parameters are the numbers that make up the body of the model that define the equations that are done on the input data to transform it into the appropriate output data. So as a reminder, what neural networks are doing is they are learning the features, they are learning what equations need to be done on the provided input data to transform that input data into the provided output labels. And so what it needs to tweak is those equations, and it tweaks them in the form of tweaking parameters. So those parameters represent the numbers that are in the equations. So the input data comes through, it's gone through a series of equations, matrix multiplications that are represented by the parameters of the model, the neurons of this neural network, and then it is transformed to get the appropriate output. So it's basically just like this super complex math function. But again, so an epoch is one pass through the entire training data set. Having multiple epochs, so multiple passes through the whole training data set, allows the model to refine its parameters with each pass. And it usually improves its performance on the training data with each epoch. However, I read somewhere that typically a lot of models now just use one epoch, so one pass, but I also read somewhere that if you are training on not a lot of data or a not high resource language, like, not English, and you can benefit greatly from using multiple epochs. So check that out. Batches, as we said, it's a subset of data. So you divide your full set of data into multiple batches. And this batch is just a group of examples from your training data set. It's a subset of the training data set. But if you only have one batch for the entire data set, then you are basically training on the entire data set. So one iteration, one update of the model's parameters is also equal to one epoch, because with only one batch, that batch consists of all of the data examples. So batches balance computational efficiency and accuracy of the gradient estimate. So the gradient is the true direction of minimal value of the loss function. So again, when we're working with neural networks, we have this idea of a loss function where You want to find, it's a super high dimensional equation, but you can kind of visualize it as like a 3D topographical map. And at the minimum, actually, let's just go to the very end. I'll give you a sneak peek. There's this graph here. So you want to find, see this arrow, the lowest point. This is our, imaginary loss function. And say we're starting here at the circle, and at each step, we want to just move towards the minimum of the loss function and ultimately get to these bottom points. Perhaps one of these is lower than the other. One of these is the global, one of them is just a local minimum. Local means it's the smallest in, its little area. Global is across the entire function, the entire graph. It is the lowest point. That's global. Anyway, so this gradient is the direction of all variables towards the smallest point. And you make an estimate of the gradient every time you are updating the model's parameters. You see, how well did I do classifying this input data into the output data, and you can learn from that, how well you did or how wrong you were. You can learn to update the model's parameters to, again, move towards this minimum point. But that's actually just an estimate of the true direction. So because we're not able to see the quote unquote true direction, because we don't have every possible example that the model could look at, it's always just kind of an estimate. It's like there's this idea that maybe out in the world there is a true function where like you're actually reaching the minimum point. But we're only getting an estimate of that because we don't look at all those data points. So when you have smaller batches, you have, as they say, noisier gradient estimates. So the direction estimate of decreasing in the loss is less likely to be accurate, less likely to be the true direction. And that is what they mean by noisy gradients. So the smaller your batches, again, the less likely you are to be going towards the true gradient, which means it's noisier gradients, but it uses less memory because you don't have to hold as many examples in your brain as you are doing these processes. And I mean you as if you were an AI model that is training. So the optimal batch size depends on the problem, the data set, and the computational resources. Like sometimes you need multiple batches because the model can't hold all of the data set at once. Having more batches also might improve regularization. So one of the issues we have is that the model is overfitting. And remember, we talked about that in day 4. And that is when the model is learning the training data too well. And so if you are looking at the entire data set every time you're updating your model's parameters, you're more likely to overfit to that data set than you are to just like look at a subset of the data set every time you do an update. As we said, iteration is one complete pass through a single batch of data, and you update the model's parameters every time you finish a batch. So an iteration is one update of the model's parameters and one complete pass through a single batch, because for each batch, you update the model's parameters. The idea is to gradually improve the model's performance through these small parameter adjustments. And again, the number of iterations per epoch is the dataset size over the batch size. So you divide the full dataset into the number of batches, and that is how many iterations per epoch. So the batch size is the number of samples in the batch. So if you have a dataset of 100 samples and you have 25 as the batch size, which means there's 25 samples in each batch, then you would have 4 iterations per epoch. So per full pass through the entire training data set, which is 100 examples, you have 4 iterations because you've divided the data set into 4 groups of 25. So the batch size is 25. The number of iterations is 4. So I just want to quickly touch on this. I said in my last video that I wanted to make a whole video on gradient descent and optimization methods, and I touch on that again at the end. But we just talked about gradient descent with this map here. Oops. right here. But there's different types of gradient descent. There's stochastic gradient descent, where you have a batch size of 1. So you update the model's parameters after each example. So you're literally looking at one example every time you do back propagation and calculate the loss and then update the model's parameters. The updates are very noisy. So again, you're less likely to actually have the true direction of the loss across all possible samples because you're only looking at one as opposed to an average or many. You don't, it's like myopic. You're not looking at the full picture of data. So your parameter updates might be noisy in that they're less likely to be the true update that you would have if you could see all possible samples. Mini batch gradient descent is when the batch size is greater than 1, but it's still less than the data set size. That's most commonly used. It balances the update frequency and the gradient accuracy. So it's less noisy, you're looking at more examples, you're more likely to be guessing the true direction of the gradient, and also it causes you to update more frequently because it is good to update frequently. Batch gradient descent is when the batch size equals the dataset size. So you have 1 iteration per epoch. This uses the entire dataset for each update. It's computationally expensive because you're looking through all of the examples for every update of the model's parameters. And you typically want to do many iterations to converge on the appropriate model parameters. So if you're going to look at all of the data every single time you want to update it, can be expensive. And also, you need a lot of memory to fit all of the examples onto your machine to be analyzed. So you have to load these samples onto the GPU or hardware that you're using. GPU is a graphical processing unit. It's why NVIDIA is so valuable right now. It makes it really easy for engineers to train models because they have these machines that do the matrix multiplications that we talked about really efficiently. You can't just train a model on your own computer. You need these special machines called GPUs or NPUs. Neural processing units are the machines that are used to train these neural networks. Anyway, you need this special model, but even those have a memory limit, so the amount of information it can store in its brain at one time, and they are very expensive. And so typically it's very hard for any machine to fit, the entire training data set in its mind at one time. So that's something to consider. Typically having a batch size equal to the data set size isn't feasible for most machines that are being used right now. So we just want to go through the steps in a single iteration of the model training loop. So the batch collector grabs a small group of items from the data set, and small is just a chosen word here, but it could be the entire data set, again, depending on the batch size, but it grabs a group of items from the data set and passes it through the network to generate predictions. The model's predictions are compared to the true labels, and then the loss is calculated, and then the gradient of the loss, so again, that direction towards the minimum of that function, the loss is that function we saw, that topographical map. The gradient of towards the minimum of that graph is passed back through the model, and then each parameter of the model is updated so that the next time the data goes through, we think we're moving closer and closer to reaching that minimum. So, steps 1 to 4 here represent a single iteration, right? So it's the forward pass, the loss calculation, the backward pass, and the parameter update. And then the next batch goes and the process repeats. And then when all training data samples have been passed through, that completes one epoch. And then there might be more than one epoch. So then the process might reset. And so that's basically it. That's the loop that we're talking about. So yeah, we have this loop, and then we do it again for as many epochs as there are. And we will discuss the validation and evaluation metrics in the next section, which is day 6. I want to quickly touch on regularization, which we did talk about in last week's video, but we'll just quickly review it, and we'll talk about some new things. So again, regularization helps prevent overfitting by adding constraints to the model. So it basically is able to smooth out the curvature of the model so that it's less fit around the training samples. So we looked at the graph of that last week, and basically overfitting is when the model just learns the training data too well and it's not able to generalize to new unseen data because it's learned certain features of the training data that actually doesn't really prove helpful actually in the real world. It doesn't actually generalize to unseen examples. It's learning special things that, aren't actually helpful. So regularization is a way to improve generalization of the model's performance outside the training data set. So we talked about dropout. When it drops out neurons, we'll quickly look at a graph of that. We talked about data augmentation when it creates new training samples. So we can rotate the training samples, things like that. I think actually maybe we talked about that in the data week. I can't remember, but it's in one of the earlier episodes. And yeah, that's applying transformations to existing data so that you have more data to train on, so you're less likely to overfit because you're looking at more varied data, you have more examples. Increasing your number of training samples can increase generalization of the model because it's just seeing more things. It's not learning something. So for example, if you only have 2 images of a cat and a dog, and in the cat, there's a cat image, there's a red splotch behind the cat, the model might learn that the red splotch is associated with a cat. But when it goes out into the real world, that red splotch isn't there and it may not perform as well. However, as you add more examples, that red splotch probably isn't going to be there, or it might have a different background or whatever. It's able to generalize better. It's able to realize that red splotch doesn't actually indicate that it's a cat. That actually isn't relevant information. So the more training data examples that you see, it's going to perform better outside of the training set. So lasso regularization adds the absolute value of the weights to the loss function. We don't need to go into the equations here. I don't think that's necessarily important. What this does, though, is it encourages sparsity by pushing some weights to exactly 0. So the weights represent the importance of a certain feature. So, you have the model learning features based on the data. It's learning, there's a red splotch behind you. And it eventually, what L1 regularization does is it forces the model to make some features just meaningless. It forces them to kind of drop out these features. And so what that does is it makes the model learn what features are actually the most important. And, kind of like Occam's razor, what is most likely to be the cause is the cause. And so by reducing the number of features the model has, it is most likely to keep the features that actually matter, as opposed to the ones that may not actually play a role in the real world, like that red splotch in the background. So L2 regularization. So this is a different equation. It adds the squared value of the weights to the loss function, but the effect that this has is it prevents any weight from becoming excessively large. So again, the weights represent the importance of a certain feature in the model's decision-making process, and it prevents that feature from becoming super important. So it just pushes the weights down so that they're more evenly distributed. And so that just causes the model to not rely too heavily on any one certain feature. And, just in case that feature isn't actually super important, or if it doesn't exist out in the real world, it makes it kind of spread across the features a little bit better. And this is generally preferred if you don't need sparsity in your model. So having a sparse model reduces computational complexity and, reduces the number of features. But if you don't need that, and you're actually okay having lots and lots and lots of features, then regularization might be good for you. So dropout regularization is when it randomly drops out a portion of the neurons during training. So we can see here, we had, 12 neurons, and now we've dropped out 50% of them. So at each layer, it drops out 50%. And that's kind of I like this analogy, like a company where team members occasionally miss meetings, forcing others to step up. So it's you never know which one isn't going to show up or which is going to drop out. And so you need to actually distribute the learnings across these different neurons rather than making any specific neuron or specific weight super heavily important. So this only happens during training. but during inference, so out in the real world, once the model is done training and is ready to go do its job out in the real world to take in inputs and make outputs, all the neurons are used. But during training, we have this dropout to force all of them to kind of step up and all of them to be seen and like have to carry some of the weight, pun intended. I'm going to make another video on optimization algorithms and gradient descent. So gradient descent is an optimization algorithm that are used to minimize the loss function. It updates the weights in the direction that leads in the steepest descent. There's certain types of optimization algorithms that are variations on just typical classical gradient descent, like stochastic gradient descent and Adam. But these help improve convergence, which means the ultimate approach and arrival at the minimum, and performance. So how quickly it gets there. So these algorithms use variations of learning rates, momentum. We talked about learning rates last week, and we can talk about momentum when we do this video on optimization algorithms. And I actually, maybe, I haven't told him this, and so who knows, but maybe I'll be able to have my old advisor, or still friend and advisor, Michael Kogendorfer, who teaches at Stanford. He's a Stanford professor. He teaches algorithms for optimization at Stanford, and he also has a book on algorithms for optimization. So, it just shook a little bit there. And so here's his book on it. I'm just, repping him right now. But he's great. I bought it right when it came out. But this is a great book. And it's out in many languages. I think it just came out in, did it just come out? I forget what language it just came out in, but so check it out. All right, everyone. Thank you so much for being here with me today. I hope that you learned a lot. Please leave your questions in the comments. I love to read them and help you learn. This is super important to me. And I hope you now know a lot about training and training processes. So again, leave your questions below. I look forward to seeing you here next week when we talk about evaluation metrics. So how do we actually see how well a model did during training and how do we improve it going forward? Also, today there was an important announcement. This morning, I released the teaser for my new series, Isabel Bemeke, who is the world's leading nuclear electricity influencer. And I will be doing a joint series, I think it's the 10 Days of AI and Nuclear, something like that. I forget what I called it. But we are doing a new series and it's going to be 10 days. And we're so excited because I actually just was kind of informed about how serious the use of energy is in training models and in using these models. So I don't know how that evaded me for so long, but it kind of just entered my field of how important it is, my field of view, how important it is. So I'm excited to dive into that with you and see how nuclear can potentially solve that. So excited to have Isabel with me and excited for you to learn from her. She's lovely, she's brilliant, and she has so much information for you to learn from. So check us out here. We will be on Instagram and TikTok, and I think we'll also have a long form video to be determined, but yeah, so see you soon. Looking forward to the series and looking forward to seeing you here next week. Have a good weekend and take care. Let's talk about an AI risk that we don't talk about enough. We know about extinctionism, so the risk that AI might literally kill all of humanity. We know about it being a black box, so they're hard to interpret it. We don't know why they make the decisions that they make. And we know about bias in data, so AI models can reflect cultural biases that exist today. But there's also an issue that we don't talk about enough, and that is energy consumption. Even Sam Altman, CEO of OpenAI, said recently, "I still don't think we really appreciate the energy needs of this technology." And he said that without a breakthrough, we probably aren't going to be able to advance AI that much further. So how do we meet the extraordinary energy demands of AI without burning more fossil fuels?
We just build more nuclear electricity.
I'm partnering with the world's leading influencer in nuclear electricity, Isabel Bimiki. We're excited to do a series with you guys on nuclear x AI.
It's going to be a 10-day series where we're going to talk about AI energy needs, how nuclear electricity works, and how they can both help each other.
And we're going to host a live Q&A, so stay tuned. We're really excited to be working together, and we'll see you back here for day one very soon.